In this video tutorial, we'll talk about page replacement algorithms. Page replacement algorithm. The main objective of a good replacement algorithm is to achieve a low page fault rate to ensure the heavily used pages stay in memory. Evaluation of algorithm is on a particular string of memory references called reference string. The reference string. It is a sequence of pages being referenced. If the user has sequenced the following addresses, then the page reference is 126.12.00. The following graph shows the page fault versus number of frames. As the number of frames increases, the page fault decreases. FIFO is the oldest page in physical memory is the one selected for replacement. The implementation of FIFO is very easy. We make a list, victims are chosen from the tail, and the new pages which comes in are placed at the head. If for the given reference string, if we choose 3 frames in the memory at a time, then we get 9 page faults. If we select 4 frames in the memory, then we get 10 page faults. Thus, FIFO replacement algorithm manifests Biletti's anomaly, that is, more frames gives more page faults. The issues with the FIFO policy: it is a very poor replacement policy. It does not consider page usage, thus it is very less preferred. Now we will see the FIFO page replacement algorithm implementation for the following string reference. First, the page is empty, so when 7 comes, there occurs a page fault. Now when 0 comes, again the page fault occurs. Similarly for 1. Now when 2 comes, there occurs a page fault and it replaces 7. Now 0, there is no page fault. 3, it comes and replaces 0. 0 replaces 1. Again a page fault occurs and 4 replaces 2. Now when 2 comes, it replaces 3. Now when 3 comes, it replaces 0. 0 replaces 4. And here 3 is already present, so no page fault occurs. Similarly for 2, no page fault occurs. Now 1 comes, it replaces 2. Now 2 comes, it replaces 3. Now 0, there is no page fault since it's already present. Now 1, it's already present, so no page fault occurs. 7 replaces 0. And again 0 comes and it replaces 1 and a page fault occurs. Now when 1 comes, it replaces 2. So in total we have 15 page faults. Thus FIFO page replacement algorithm is very poor page replacement algorithm.
Now we are going to see optimal page replacement algorithm. This page algorithm guarantees the lowest possible page fault rate for a fixed number of frames. The concept behind this algorithm is the page that is not going to be referred for the maximum amount of time will be replaced. Now let us take an example. We have been given a sequence of page and we are going to apply this algorithm to it. Initially our memory is empty, so we can directly replace 7, 0 and 1 into the memory. Now 2 will come and we will check that a page that is not going to be referred for the maximum time will be replaced. So we check that 0 and 1 are going to be referred before 7, so we are going to replace 7 by 2. Next 0 will come. We find that 0 is already present in the memory, so there is not going to be any page fault. Next 3 will come and again we will check that 0 and 2 are already present before 3, so we are going to replace 1. Then 0 will come and we find that 0 is already present inside the memory, so there is not going to be any page fault. Now for 4 we will again check that 2 and 3 are going to come and referred before 0, so we are going to replace 0 by 4. Then next 2 will come. It is already present inside the memory, so there is not going to be any page fault. And next 3, the same, it is already present, so no page fault. Then 0 will come. We find that 4 is not referred for the maximum amount of time, so we replace 4. Now 3 is already present in the memory, so no page fault. Next 2 is also present in the memory, so again no next page fault. Now in case of 1, we see that 0 and 2 are going to be referred in the near future and 3 is not going to be referred for longest period of time. So we replace 3. Now for 2, it is already present in the memory, so no page fault. 0 is also present in the memory, so no page fault. Same with 1, no page fault. Now for 7, again we will check that 0 and 1 are going to be referred in near future. So we are going to replace 2 by 7. Next 0 will come. We will check that it is already present in the memory, no page fault. Again 1 is present in the memory, so no page fault. Now we see that in this example, number of page fault is 9. So the miss ratio for this will be 9 divided by total number of page reference, that is 20. And hit ratio will be 1 minus miss ratio, that is 11 by 20. Now although this algorithm might be the best algorithm for page replacement, but it has certain disadvantage. In this we assume that we already know the future requirement of pages, but in actual it is not possible to know about the future requirement of pages as before. So even though the optimal replacement algorithm is very efficient, but it is difficult to implement in real scenario. So that was all about optimal page replacement algorithm.
Okay, so till now you read about this FIFO and optimal page replacement algorithms. Now let's look at this LRU page replacement algorithm that is recently used. So what it does is it replaces the page that has not been referenced for the longest time. By the principle of locality, this should be the page least likely to be referenced in the near future. Also, it also performs nearly as well as the optimal policy. Now let's see how it works. This is our reference string. This is a frame of size 3, and this cross shows a hit. Okay, so initially this 701 will be filled in the empty spaces like this, and this cross will show a hit. Okay, so next comes this 2. Now this 2 will replace this 7, and since it's a least recently used, and this 0 and 1 are comparatively more recently used. Next comes is like this. And next comes is 0. This is already there in the frame, so will not replace anyone, then it will be a miss. Next is 3, and 3 will replace this 1 as it's a recently used. Next is again 0, it's already there, so it will be a miss. And next is 4, so it will replace this 2 as it's recently used. Okay, and it's a hit as it replaces a page. The next is 2, and it will replace 3 as it's recently used. Similarly 3, and then the 0, then 3 already there, so it's a miss. Then a 2, it's already again there, so it will be a miss. Then 1 will replace this 0 as it's least recently used compared to the other 2. Okay, the next is 2, it's already there. Next is 0, it will replace 3. Next is 1, already there. 7, it will replace 2 as it's the least recently used. Next is 0, already there. 1 is also already there. Now I would like to tell about some facts about this LRU policy. The LRU page is the one with the smallest time value, that is needs to be searched at each page fault. So this would require some expensive hardware and a great deal of overhead. Consequently, very few computer systems provide sufficient hardware support for true LRU replacement policy. Other algorithms are all used instead. I hope you got the idea of how it works.